Welcome to this deep dive explainer. If you are ready to unravel a beautifully complex mathematical mystery today, well, you've landed in exactly the right spot. We are setting the stage for a high-level mathematics tutorial, and we're going to prove what looks like a deceptively simple algebraic anomaly. We're going to explore how a problem about polynomial roots can actually unlock an entire universe of connections between p-adic lifting, the rigid architecture of unramified automorphic representations, and literally the fundamental fabric of quantum physics. Let's get into it.
Before we tackle the really dense equations of the Langlands program, here is our quick roadmap. 1. The hero equation. 2. The characteristic P obstruction. 3. The Adelic pipeline. 4. Koszul homology. 5. Quantum coherent states. And finally, 6. The Hasse-Schmidt solution.
All right, let's jump right into part 1, the Casas-Alvero hero equation. Okay, let's dive into this foundational puzzle. What we're looking at is a visual map of unramified automorphic representations, and honestly, this structure forms the absolute backbone of everything we're about to discuss. To solve the Casas-Alvero conjecture, we literally have to reformulate a classical algebraic problem into an entirely new framework, utilizing the Adelic Langlands Program. Think of this as our architectural blueprint for translating local polynomial roots into massive global rigidity.
So here is the absolute crux of the classical problem. The Casas-Alvero conjecture throws down this amazing constraint. If a monic univariate polynomial, f(x) of degree d, over a characteristic zero field, shares a non-trivial common factor with every single one of its first d-1 derivatives, something incredible happens. It suffers what we call an absolute collapse. Because it shares roots with all those derivatives, it's forced to become highly rigid, collapsing entirely into the form of a pure power. F of x equals x minus alpha all to the power of d. It's a beautifully simple hero equation, right? But mathematically proving it, notoriously difficult.
Which brings us to part 2, the characteristic P obstruction.
Now, you might be wondering, why exactly is this so difficult to prove? We really have to ask ourselves, why does classical mathematics just fail to solve this deceptively simple equation? I mean, if it's just about polynomials and formal derivatives, why hasn't traditional algebraic lifting cracked it by now? Well, the answer lies in a terrifying bit of mathematical terrain known as bad primes.
The whole thing basically falls apart in positive characteristic P. Take a look at the equation, f of x equals x to the power of p. If you try to take the formal derivative of this inseparable polynomial, it just vanishes identically. It becomes 0. And that creates a fatal division by 0 error, completely blocking our ability to lift the proof back up to characteristic 0. It's kind of like trying to build a house, and suddenly your entire concrete foundation evaporates into thin air. These bad primes cause dimension drops and algebraic anomalies that our traditional strategies just cannot bypass.
So how do we fix it? That's part 3, the Adelic Langlands pipeline. To bypass this completely insurmountable obstacle, we pull out a multidimensional master key, which is the Adelic Langlands Program. By mapping the polynomial into an arithmetic scheme, we embed it across all p-adic local fields using Satake parameters and translate it into a Galois monodromy representation. From there, we finally map it to a dual automorphic state. Basically, by tracking all prime places simultaneously, we use local global compatibility to force those chaotic bad primes into total global alignment. Let's look at the specific mathematics of that embedding. In step A, we translate the problem to ideal heights. The intersection resultants of the polynomial and its derivatives have to satisfy a strict height condition, which forces a one-dimensional variety of pure powers. Then, in step B, we lift this into an Adelic Galois representation, mapping it to GLN of the p-adic numbers. The shared roots completely dictate the local monodromy behavior. Any algebraic anomaly, or let's call it an almost counterexample, acts as an arithmetic twist, and mathematically this registers as a local ramification event, meaning its conductor exponent, fp, is strictly greater than 0 at those bad primes. And this brilliantly illustrates the real magic of the global functional equation. Through the Langlands correspondence, we evaluate the global conductor, n of pi, which is just the product of all those local ramifications. Because the Casas-Alvero condition demands a shared factor with every single derivative, the intersecting derivatives form this incredibly tight, closed algebraic loop. The global wave harmonics of the ideal ring regularize the bad primes. It smooths out all that noise, forcing the global conductor to decay to exactly 1.
So, in plain English, the math smooths out the chaotic bad primes into absolute perfect harmony.
Now, I want to slow down just a bit here because we really need to appreciate this rigorous resultant to spectral identity. Notice that determinant equation. The information stream is totally conserved across all local field completions. Because a global conductor of 1 literally cannot accommodate local ramification at any prime, the arithmetic variety collapses onto a singular unramified orbit. And that mathematically guarantees exactly one root in its algebraic closure, which gives us the definitive proof that f of x equals x minus alpha to the power of d.
Let's look under the hood. In Part 4, Internal Engine, Koszul Homology. Mechanically speaking, how does this closed loop actually operate? Well, in the Adelic Langlands program, a sequence of geometric intersections isn't just analyzed as some static set of points. Instead, we use Koszul homology to treat it as a flowing chain complex. If you trace that visual funnel starting from the derivative chain of length d-1, we apply a differential operator driven by the formal interior multiplication of the derivative sequence values. Eventually, we arrive at the homology modules. This whole homological structure is what dictates the local global behavior of the entire wave field.
Next, we push this complex through the Grothendieck-Riemann rock push-forward, the GRR. This embeds those homological modules directly into the representations of the Langlands dual group. Take a look at that matrix visualization of operator E. Because our polynomial shares a root with every single derivative, the differential operators map perfectly to a regular nilpotent operator E. And this creates a single, unbroken Jordan block of size d that spans the entire dual space representation without ever snapping.
This leads to an absolute systemic structural collapse. Check out that massive commutation constraint equation, where the local Sadike matrix, A, rho, P, and the regular nilpotent element E must equal 0. In representation theory, the only matrices that commute with a regular nilpotent element are polynomials in that element itself. And since Sadike parameters have to remain semi-simple, all those non-diagonal degrees of freedom just instantly vanish. The Sadike parameters collapse entirely into a single scalar value across all finite primes, which utterly eradicates any possible room for counterexamples to form.
This takes us into some wild territory in Part 5, Quantum Coherent Ground States.
Let's explore the profound physical interpretation of this math because it's fascinating. Here, the derivatives actually act as geometric waves. As you can see, the master wave packet F is perfectly synchronized with every single one of its internal, higher-frequency harmonics, the derivatives. When the system is forced into the continuous Archimedean infinity, those discrete local anomalies lose their stable energy anchor. The math proves that a wave packet synchronized with all its derivatives has absolutely zero radiative dispersion, no internal leakage whatsoever. It acts as a pure absolute geometric point source.
We can actually map this directly to a multi-frequency quantum harmonic oscillator. Look at the graded annihilation operators there, representing higher-order differential transitions. The Casas-Alvero condition acts as this absolute quantum filter, basically freezing out the chaos. Because the higher-order Koszul homology modules vanish, there are simply no quantum transitions between energy levels. It completely stabilizes quantum chaos, proving that the pure polynomial power, that equation you see at the bottom, is the exact mathematical shadow of a multi-frequency quantum system locked into its unique, non-dispersive coherent ground state, minimizing Heisenberg uncertainty.
Finally, we arrive at Part 6, the Hasse-Schmidt solution. As we hit the final stretch of this explainer, we have to talk about how this framework survives the jump between analog and digital mathematical spaces. Earlier, we talked about the total failure of classical differentials at non-zero characteristics. You can visualize this like a snapping chain. In positive characteristic P, the classical derivative relies heavily on factorials. When the derivative order is greater than or equal to P, it introduces a factor of P, which drops the operator's rank identically to 0 modulo P. This division by zero blackout is the mathematical equivalent of hitting a solid brick wall at light speed. It literally snaps the causal chain, which theoretically would allow chaotic, anomalous quantum states to form at finite scales.
So how do we fix a snapped chain? We replace the classical derivatives with Hasse differentials, or Hasse-Schmidt derivatives. Notice the binomial coefficient in that top equation. This coefficient evaluates as a clean integer before reducing modulo P, which means it safely bypasses the factorial vanishing issue by tracking Taylor expansion coefficients instead of limit-based rates of change. Below that, the regular nilpotent element E is replaced by a Frobenius twisted counterpart. This highly robust framework locks local polynomials into restricted, pure geometric powers, totally preventing any arbitrary counterexamples at the microscale.
I really love this table because it beautifully synthesizes the whole transition we've been talking about. On the left, in characteristic 0, we have the analog universe. We're talking smooth, continuous fields, classical differentials, and everywhere unramified baselines, which all produce a global macroscopic wave. Then, on the right, in positive characteristic P, we drop down to a digital quantum substrate. This is made of discrete Galois fields, governed by Hasse differentials and Frobenius twisted restrictions, resulting in a localized quantum code block. It is just a perfect, elegant translation from continuous spacetime right down to discrete Planck scale boundaries.
Which brings us to our final unifying thought for this explainer: focus on the concept of Adelic error correction. The global functional equation basically weaves these digital local codes back into the continuous Archimedean infinity, and it uses Hasse factorials as a built-in error-correcting code. It stops local phase anomalies from leaking out into the macroscopic universe. So, I want to leave you with this provocative thought to ponder. Are the smooth, continuous physical laws of our universe actually governed by a hidden digital arithmetic framework? Because looking at the mathematics of the Casas-Alvero conjecture, it strongly suggests they just might be.